McQueen here, and I use Rusty's medicated bumper ointment, new rear end formula. Nothing sues a rusty bumper like Rusty's. Wow, look at that shine. Use Rusty's, and you too can look like me. Ka-chow!
Ka-chow! Hello, everyone. I'm Craig, and I can't know what is going on here. Okay, let's put the clicker down. All right. Hi, I'm Craig. It's a really pleasure to be here. If you want to follow along with these slides, grab that QR code. Might be easy to read them on your phone or whatever. I'm from New Zealand. I'm an Angular GDE, and I'm part of the engineering team at Rust-eze. We're based out of Lightning McQueen's headquarters in Radiator Springs, Arizona, and we're responsible for making sure that Mr. McQueen is performing his absolute best to keep up his winning form. Lightning McQueen. It's a bit of a legend around these parts. 7-time Pistol Cup winner, catchphrase master, and all-around good guy. Whatever Mr. McQueen wants, Mr. McQueen gets. And usually what Mr. McQueen wants is to go faster. Lightning's a highly tuned machine. Every system is engineered for peak performance, and we're always on the lookout for ways to make him go faster. Our chief engineer, Sir Tomato, has been Lightning's best friend for as long as anyone can remember, and he's often the source of the best ideas and suggestions for how to make things go faster. Speak of the devil, here he comes now.
Hi there, Craig. I have an idea to help Lightning McQueen go even faster.
Oh, that's amazing, Mater. What's the idea?
I think it's time to get the aerodynamic simulation working on Lightning's heads-up display.
Wow. Great idea, Mater. We've always wanted Lightning to be able to update his aerodynamics on the fly during a race. A little known fact about Lightning McQueen is that all of his onboard software is actually written in Angular and running on his internal browser while he races. Lightning uses complex aerodynamic simulations to figure out the fastest shape to be in while he's racing. These simulations use what's called a lattice-Boltzmann method to simulate the flow of air over the body of a car. It is working. Cool. This is an example of the kind of visualization that the simulation produces. The lattice-Boltzmann method is a two-step algorithm which models how fluid moves through a space and how it interacts with barriers in that space. The first step is what's called the collision step, which models the change in fluid density over time. And the second step is what's called the streaming step, which models collisions between molecules in the fluid. The specifics of how this works and the implementation details don't really matter here, and it does take quite a bit of math to make it work. But at a very high level, you can think of it as like a simulation across a 2D space.
We just need to figure out how to get the simulation running fast enough to be useful during a race.
Yeah, that's right, Mater. Whenever we've tried to run it in the browser in the past, it just hasn't been fast enough. Crunching all those numbers, it takes some time. So let's dig into it a little bit more. There's two main parts to our visualization. There's the simulation and then the rendering of that simulation. The simulation class is the actual implementation of the lattice-Boltzmann algorithm, which takes x and y dimensions for the grid, and then some values that represent velocity and viscosity and the simulation speed. The canvas renderer class is just an HTML canvas-based renderer which colors in the grid based on the velocity at each point in the simulation. Everything just executes in a loop, so we do one step of simulation, and then the result of that is drawn to the canvas. The full Angular implementation of this is in that chunk of code, which you definitely can't read, but scan that QR code and you'll be able to have a closer look at that if you want. The end result looks a little bit something like this. As we can see, it's like a little janky and it doesn't quite run as fast as we might want for it to be truly useful. And if we add some time logging, we can see that our simulate method is taking about 32 milliseconds a frame. If we want to hit 60 frames a second, then we need to be hitting about 16 milliseconds a frame, or we need to be twice as fast. But the good news is that our render code is pretty damn quick. It's running at about 2 milliseconds. So our rendering code is good, Canvas APIs are fast, but the simulation code is too heavy to get it running at 60 frames a second.
We don't know if it's fast enough for me to use it in real time. I need it faster.
Sorry, Lightning. You need it faster.
You hear the boss.
You're the boss.
Gotta be faster.
You get to work on that. I need to go put on some Rust-eze. Ka-chow!
Ka-chow! If there's one thing I know about Lightning McQueen, it's that he sure loves Rust-eze. Wait a minute. That's a great idea. Rust. What if we try writing the simulation in Rust?
Woo! That's a great idea.
Thanks. I think so.
You'll have to teach me a bit of Rust so I can help.
Of course. Let's do a quick comparison between TypeScript and Rust. So TypeScript is a superset of JavaScript focused on static types and web development, whereas Rust is a systems programming language emphasizing memory safety, performance, and concurrency. TypeScript relies on the JavaScript runtime and the garbage collection of that world, whereas Rust provides memory safety without ever using a garbage collector. TypeScript supports asynchronous, event-driven programming, but lacks native parallelism, is a hard word, while Rust has built-in support for executing parallel code and doing concurrency. Rust offers fine-grained control over memory and is able to produce really high performance by being a compiled language, whereas TypeScript inherits JavaScript's inherent performance characteristics. In TypeScript land, we might use something like NVM to manage our node version, and the Rust equivalent of that used to install Rust is something called Rust up. For TypeScript, we might, or more generally Node, we use something like npm to install dependencies. In Rust, we might use cargo to install crates. To compile code in TypeScript, JavaScript land, we can use a number of different tools. In Rust, we're generally going to use cargo build. Similarly, in TypeScript land, we have a whole bunch of different tools that we can use to test our code, but in Rust, we're going to use cargo test. In general, Rust has a much tighter coupling between the language and the tooling.
Well, that's all pretty neat, but what does it look like?
That's a great point, Mater. Let's have a look at some code. So we're hopefully pretty familiar with what assigning variables look like in TypeScript, where we can create variables with const and let, and there are some rather confusing implications about mutability with the values that are assigned to those. This is the rough equivalent in Rust. So by default, we use let, and a variable is immutable. And if we want to opt into mutability, we need to use the mute keyword, and that says this thing might change in the future. For like importing code in TypeScript, we can just import from other files. Using relative paths, or if it's a node package, we might use a full name. And a TypeScript file is just interpreted from the top down, line by line. In Rust, there's not necessarily a one-to-one mapping from files to modules. But we can import a full module and move specific module members into scope using the use keyword. The entry point for a Rust file is usually the main method. And we can emulate something like instantiation by calling a new method. This is just a convention, though. It's not part of the language like the new keyword is in TypeScript. TypeScript, of course, has control flow structures like if and while, and also, you can call functions. And when we pass things to TypeScript, you're always passing a reference to that object. Rust has things that are roughly equivalent, but there are a few syntactic differences, like you don't always need to use braces in Rust. But they mostly work as you would expect. However, when you're calling a function in Rust, you need to explicitly state that you're passing a reference by using the ampersand. I'll talk a bit more about this soon. Of course, TypeScript has functions, and there's a whole bunch of similarities between functions in TypeScript and functions in Rust. Rust uses the little fn keyword to define a function rather than the full function. and has some differences with the naming conventions. So we're going to use snake case instead of where we might use camel case in TypeScript. Rust allows us to be a bit more specific about the parameters that we're going to pass to a function and how they can be constrained. So you can say that a thing must be passed as a reference, or that it must be mutable, or in this case, that it must be a mutable reference. Another little difference is that Rust has more specific number types. So in this case, in the TypeScript side, we just had the generic number, and here we're talking about a U64, which is an unsigned 64-bit integer. And one little bit of syntactic magic that Rust has is this kind of special syntax for creating ranges, which might look familiar if you've ever done like list comprehensions in Python. TypeScript lets us define object shapes by using types or interfaces. And the equivalent of that in Rust is a struct. By default, everything in Rust is private, and you have to be explicit about the visibility, in this case marking things as public with the pub keyword. And again here we can see those slightly more specific number types. In TypeScript, you can define a class which is both a type and the implementation of that type. Whereas in Rust, these things are always separate. The type is defined as a struct, and again, in this case, we haven't marked them as pub, so they're private by default. And then we use the impl keyword to define an implementation of that struct. Here we can see we're using this new function, this convention, to kind of look at like something like an instantiation. And it's going to return something that maps to the type of that struct. One other little interesting bit of syntax here is we have this vec bang syntax, which is what's called a macro. And a macro is a way that you can do metaprogramming in Rust, which is code that generates Rust code.
Gosh, that looks like a programming language.
Exactly, Meta. There's nothing too scary here, especially for just converting something like our algorithm that's just kind of a bit mathy. So here's the TypeScript implementation for the simulation. This is just the first chunk of it, and as you can see, it's just doing some looping over some arrays and adding up some numbers and assigning them around. You can check out the full implementation at that QR code if you want. And here is the equivalent in Rust. They look pretty similar. Translates fairly straightforwardly from TypeScript into Rust. The main difference is we've got some different syntax for looping over lists. We're using the self keyword instead of this. And we've got a bit more precision around the different types of numbers that we're using. It would actually be pretty easy to compare these two bits of code and kind of go, okay, what's actually special about Rust? And most of the magic is in the realm of memory management. So Rust guarantees memory safety without garbage collection by enforcing some basic but strict rules for how you pass data around. Basically how you borrow data from one place or how you transfer ownership of who owns the data. Let's look at ownership first. Let's say we really want to initialize our simulation twice, just to be extra safe. If we pass the simulation to these this function 2 times. And if we were to run cargo build, so that build command over this code, we get a big fat error. Rust compiler errors can seem pretty daunting at first, but they're actually really helpful if you read all the details. It can often mean like Googling or looking up in the docs a bunch of big scary keywords, but it actually kind of tells you what's going on. And what this error is saying is that when we pass the simulation into the initialize function the first time, we gave up ownership of it. And so we didn't own it anymore, so we couldn't give it away again. It'd be like selling a car twice. If we want to be able to give away ownership twice, we have to first clone our object. So we have to create a new instance in memory, and then we have 2 things that we can give away. And in this case, the borrow checker would be happy. But sometimes you don't actually need to transfer ownership, and a function can ask to borrow the object. This basically means that the function is going to expect a reference to an object of a given type, rather than the object itself. The calling code can take a reference of an object by using this ampersand symbol, and then it can pass that reference to the function. This is similar to how object passing works by default in JavaScript or TypeScript. And you can make as many immutable references as you want, but initial barrier, that function, actually expects a mutable reference. And if we try to take a second mutable reference and then pass it to each of these functions, we've broken another rule. But again, we get a really useful error message, and Rust kind of tells us exactly what the problem is. The fix for this is a little bit frustrating. So we can take the first mutable reference and then use it, and then take a second mutable reference and then use it. Once we do it like this, we get a happy compiler. And it's a little bit weird to fix a compiler issue by just moving a couple of lines of code around, but it's kind of important to remember that JavaScript, TypeScript, these languages have weird quirks, and we got used to them, so it's kind of something we can just get used to here too. While the borrow checker is like pretty different from anything that we see in TypeScript land, the concept of type checking is pretty familiar. But that said, there are a few differences between TypeScript and Rust. TypeScript has what's called a structural type system. If two objects have the same shape, they can be applied to the same type, regardless of what the types are named. This arises from the inherently duck-typed nature of JavaScript, and if two things look the same, they kind of behave the same. But Rust, on the other hand, has what's called a nominal type system. Two types are only the same if they use the exact same name. So they could be totally identical, but they can't be applied to the type, even though they've got the same structure. TypeScript has a relatively simple number type. Originally, it was just the generic number, and more recently, we've had this big int type. But like I've kind of mentioned, in Rust, there are a whole bunch of different number types. So we can have signed or unsigned integers of different bit lengths, or floating numbers, or we can have this usize, which can be used for indexing. Thankfully, booleans are the same in these languages. There's not some magic third boolean value in Rust. But strings, again, get a little bit more complicated. TypeScript just has strings, but in the Rust side, we have this uppercase string, we have a lowercase str, and then we have the character type. The character type just refers to a single character. It's almost analogous to like a single character, what do you call it? Constant type, literal string type in TypeScript. God, I can't remember words anymore. TypeScript, we have arrays. This is a generic type, and the equivalent in Rustland is a vector of this type. And like we talked about before, in TypeScript, we have objects and classes with types and interfaces. In Rustland, we have structs and implementations.
Okay, so let's write the renderer in Rust.
Hell yeah. That's a great idea. Let's give it a go. So let's take a look at the TypeScript implementation first. The canvas renderer just has a simple single function called paint, which takes a simulation. It loops over each position in the simulation grid and tries to decide what to do with each cell position. If a cell is a barrier object, it's just going to paint that cell black, which is pretty straightforward. Otherwise, it's going to look up the value of the velocity at that point in the grid and paint the grid position the appropriate color for that velocity. For performance reasons, the color square function kind of creates an image and updates individual pixels in that image, and then at the end of the paint function, the full image is inserted onto the canvas. Now obviously Rust doesn't have an HTML canvas API, so we're just going to write to the terminal. The terminal renderer has a single function called paint. It starts by sending some terminal control characters that clear out the terminal and then reset the position to 0. And then we create an uppercase capital letter string type, which means that we can define extra characters to the string as we go. Again, we loop over the whole grid, and if it's a barrier token, barrier position, we just assign a black square to that point in the terminal. Otherwise, again, we look up the color for the velocity, and we assign that. So don't worry too much about the code. For each line, we append a new line just so that we can render a grid. And then at the end, we push the whole thing to the terminal. We can do an optimized run using cargo run with the release flag and get something that looks like this. So our Rust implementation is way faster. So each step of the simulation, I don't know if you can read at the bottom, is taking around 600 microseconds. So a hell of a lot faster than our TypeScript implementation. And while our terminal renderer is much more granular than our nice canvas renderer, we're still able to perform the whole simulation and the rendering function much faster than the canvas renderer could render a single frame. So I think it's safe to say that the Rust implementation of the simulation is definitely certified faster.
Ka-chow, did someone say faster?
Sure did.
You three, she's flaming hot now.
Flaming hot.
Whoa. How can we get that running that fast in my browser? Ka-chow!
Ka-chow. Well, Mr. McQueen, the Rust ecosystem has one more magic trick for us to try out. So WebAssembly has been floating around as an idea for a few years now, but the Rust ecosystem provides probably the most complete and accessible ways of creating WASM bundles that can run in the browser. With just a few changes to our code, we can prepare it to be compiled to WASM. First, we need to import the WASM bindgen module, and then add a few WASM bindings to expose the relevant parts of our code to the compiler, using this kind of weird syntax, which is somewhat similar to like a decorator in TypeScript. We can then step away from cargo for once and use WASM pack to build a WASM bundle of our Rust code. Working with the compiled WASM code from the TypeScript side is a little bit weird. So we can just import it like normal, but of course we produce this from Rust code. So we have to kind of follow these new Rust conventions. So instead of creating a new simulation, we're calling that new function on the module. And we also have to make sure that we're passing the right number types. So instead of just a normal number, we're using an unsigned integer. We want to make sure as well that our simulation stays fast. And that means we want to avoid passing data back and forth between Rustland and WASMland. We could just return values, but that's quite slow. So instead, we're going to take a pointer, so a reference to a position in memory of the WASM memory, and then we're going to use one of these unsigned or these typed array classes to get a view over the memory that we care about. And we can then use that and pass that data to our canvas renderer and get something like this. So running our fancy new WASM implementation in the browser is clearly a lot faster than the original TypeScript thing. And we can get some numbers for this and log the time that the simulation takes. And we can see that we're well under our 16 millisecond target. So we can get to 60 frames a second. And so again, our new implementation is certified fast.
Ka-chow! This is amazing. I can custom tune my drag reduction system as I go.
Yeah, you can, Lightning. That's awesome.
That sounds like success to me.
Me too. Let's go over what we did one last time. So, Lightning McQueen always wants to go faster. And his dream is to be able to use aerodynamic simulations in the browser on the fly while he's running within his Angular applications. But he can only use a web browser during the race, and TypeScript is just too slow for this much number crunching and processing. But Rust is fast and can run the simulation super quick. And if we combine it with WASM, we can get it running super speedy in the browser and make Lightning a very happy car. Demo again, because it's pretty and I like showing it. Also, you can scan the code there. There is no documentation on it. So if you want to try to get this running yourself, flick me a DM or whatever, and I can try to help you. Ka-chow, the end. Once again, I'm Craig. Thank you so much for having me. Shout out to all the organizers, done a great job.